Have you ever wondered how privilege escalation actually works? Did you ever use, for example, a public exploit during one of your security assessments or while doing a pen test? And ever wondered how this actually works under the hood? There is something called process credentials. And in a lot of cases, when a kernel vulnerability is being exploited, process credentials are being exploited or being overwritten to achieve root privileges on a Linux system. And a lot of other devices are using the Linux kernel for their operating system. Learning these techniques is very essential. In today's topic, we are going to deep dive into the world of privilege escalations and learn how you can actually modify process credentials if you have a kernel vulnerability. Hello and welcome back to the channel. My name is Umit Aksu and I'm the founder and director of Mobile Hacking Lab. And in today's session, we are going to deep dive into the world of privilege escalations and specifically into process credentials. Before we deep dive into this topic in itself, let's first go back to the basics. A lot of devices, for example, mobile devices like iOS and Android, are using a Unix or a Linux core. The Linux kernel, which handles all the communication with the hardware, has a lot of privileges. So while exploiting kernel vulnerabilities, what the exploit developer or hacker is trying to do is abuse a vulnerability to change the process credentials to elevate the privileges. We also need to understand that there are two types of privilege escalation. One is a horizontal privilege escalation. We are escalating our privileges to another type of user, which does not always have higher privileges, but in the case, for example, a mobile device, this might help us to access another app's sandbox. And we also have vertical privilege escalations, which will give an attacker more privileges, for example, administrative or root privileges. In this video, we are going to deep dive and learn how vertical privilege escalations actually work. Now, in the type of vertical privilege escalation, we are abusing a vulnerability within the kernel. For example, a kernel driver give a normal user access to, for example, GPU drivers. If a vulnerability in the GPU driver happens and gives us like a read-write access with more privileges, this can be, for example, abused to modify process credentials. And today I'm going to showcase you and mimic in the debugger how a read-write primitive or a read-write vulnerability within the kernel can be abused to overwrite the process credentials. And we will do this together and you will understand how kernel vulnerabilities are achieving root privileges or elevate their privileges. So before we dive further, make sure you hit that bell button, subscribe to the channel, and also give a like and leave a comment in the comment section if you support our videos. So let's deep dive together into this topic and learn how privilege escalations actually work. So now that you are here, let's do a deep dive into this together. I have here a Linux machine booted up. This is a cloud VM that we are also using during our course. So you also have a sneak peek into the course material that we have. Now, before we can proceed, first of all, what we need to do is make sure that we have a compiled kernel. So for that, what I will do, because in this one, we have an Android kernel. If we do tab, we should see here the Android kernel. And in here, I have the Android source code. Now, within the course, you actually learn how you actually compile the Android kernel yourself. And I'll actually create another extra video where I will teach you how to build this. But it's quite simple. So once you have everything set up, before you can even compile the kernel, you need to make sure that you can configure it. In this case, my kernel is already configured, and I will skip that for another time to show you in another video how that works. But once your kernel has been built, you can now make the GDB scripts, which is very important. You need to make sure that GDB scripts are built with your kernel. Now that we have the GDB scripts, these are located in the scripts folder, as you can see over here, and we should be able to use them during our debugging session. Now, we can also see that a Linux kernel has been built over here. If I do file VM Linux over this, you should see that this is a built kernel, and we could use this kernel directly. Now I need this to be able to emulate it. So we have here a script that I'll open this for you so you can see what is in the run.sh. What this does is this will run a QEMU instance, and fully emulate this kernel for us and attach a root file system that I also built previously. Now, this is all not important for you right now to understand how the process credentials work, but you will have an idea of how the emulation works. Now, what I will do very simply, I'll first make sure that we will split our screen in a vertical way, split it also horizontally. Now we have 3 running ones. Now, what this will do, it will run our kernel, which I will do over here. Now our kernel will start booting up, and kernel debugging has been enabled on this. Now that this has been booted up, I can now log into my kernel, and you can see we are logged into our kernel. Now, in this case, what we need to do is make sure that we attach debugger to our kernel. This kernel is now listening or has kernel debugging enabled, meaning that the port 123 is open. We can now attach GDB to it. I will use GDB multi-arch for it because this is an Android kernel and we are going to use what multi-arch has. It has like all the different architectures in it, so it will make it easier to do the debugging. We also need to point it out to the VM Linux. As you noted, I'm still in the Android kernel folder and we had the VM Linux kernel there. This is so that we map the remote debugging over here directly into our GDB session. So when I press enter, it should start rolling up. And the second thing, which is very important while doing this, is we need to make sure that we can load the kernel scripts. Now you can do this by it's still loading right now. Once it's done with loading, what we need to do is do add auto load save path. This will be allowing us to load from the Android kernel folder, and it makes it easier to search for example for scripts. GDB automatically knows where to search for the scripts. So in this case, it will find the GDB scripts that are needed for this session. Now, what we can do is target remote and then 123. And we could also specify the IP address here, which is localhost, but in this case, we don't need to. But for the sake of this example, we'll add it there. But you don't need it. You can also use it without that. So press enter and you should see it recognize it. If you do it without adding the VM Linux file, it won't recognize the symbols, so you won't be able to debug in a proper way. Now that we have a connection and you can see this doesn't work. If I type anything over here, it doesn't type anymore. Once I continue, I'll press continue one more time, and you'll see that all the typing started happening. Now I'll press again Ctrl C, and it will go back and pause the process over here, which is the kernel, and we are doing the kernel debugging over here. Now what we need to do is load GDB scripts. So for that you can use the symbols and this should load all the needed scripts for this VM Linux which we built previous. Now that this is working, what you could do is type in LX because there are many other scripts included. As you can see over here, there are many other ones. For example, LXPS will show all the processes that are running. Here I can run this and you can see all the processes that are running in this kernel process right now. This will be very handy in a minute, and you can see that there is a process running right now, and that is the shell over here within this kernel. If you scroll up a little bit, you will see many other processes, and the process number 1 that you see is the init. And any other process that in the beginning when the kernel boots up, it will start booting up, and then the first process that will start is the init process. Any other process that will create it after that will be a fork or a copy of that process, and you will see that later when I'm going to show all the processes. The task structure. Now, to be able to do a privilege escalation, one of the most important things is that we need to figure out for every task that runs, there is a structure called the task structure. So this is a special structure that contains information about the process and the threads and all the other type of information, which we don't need right now. So I don't want to confuse you with too much information, but what is important is the task structs are a linked list that will contain a pointer to the previous and the next as a next pointer. So if we would, for example, get a task pointer to this, it will point to the next one, which has a point. This one will have a pointer to the next process, which will be kworker. And if it has also a previous one, so it will point to the previous, the task struct as well. That is the watchdog over it. So they are all linked to each other, which makes it also handy for us. Now, there's also always one that is always running. If we execute $LX current, we should be able to get, like, for example, if I do P $LX underscore current, and then like this, and then do PID, we should get the process ID of the running process right now. Now we are running in the context of the kernel itself. We can do LX and then tab and then use one of these commands again, like PS or any other one. We can just now continue, and in order to access a specific kernel task PID, we can put a breakpoint and then follow the script variable. So first of all, let's see how we can access one of them. So as I said, we can do this by typing $LX underscore current and then the PID. So we are accessing the current and get the PID of it. You can see that over here. If I do PX LX underscore current, we can see that there is, since it's a linked list, if we start printing all of them, we can see init task over here. And it has like all the previous pointer, and right now we are printing the one from the current one. But if we continue like this, you will see all the other task structs if we just follow all the pointers. So how do we access these process credentials? Now let's assume that we have a program and we go in here. In this case, we can go to our home, Android fuzz, home, kernel fuzzing, and then the course material. In the course material, we have the kernel driver, and there we have an application called program. Now, what I will do is do code. We have here a driver that can read and write, a simple driver that doesn't do much, just reading and writing. And there's something interesting which I put it in here to make it easy for all of us to understand this a little bit better. So there are some vulnerabilities in there, but we are not focused on the vulnerabilities as we speak right now. But this does nothing more than read and write. As you can see, read, write, and these are the ones that we are going to use. Now, I also built an application that can interact with this driver. And this driver, as I said also in the introduction videos, drivers have root access. They need to have more privileges to access like file system or to be able to modify certain things on the operating system. Now, in this case, this driver does nothing more than read and write, nothing special. It contains some vulnerabilities, but these are being discussed also during learning, which we will make videos as well. But one important thing is an application that can interact with it. Now, we have a very simple application over here. Can interact with the driver and can read and write to this driver. Now, let's look at the write one. So this sample application does nothing more than accept, for example, if we look at the beginning of this, it has a main, and it will open the device driver called Mobile Hacking Lab, and it has read, write access to it. And in this case, if it's a write, it will write the data that we write to the driver, but also open a new process. This is important. We'll test this out and we'll make sure that this works. This is running as an ARM64, so we need to cross-compile over here, which I will do right now. So we'll use ARM64 GNU GCC and then use program.c and then program to compile this. Now, once this is compiled, we need to transfer it over here, so I need to continue this process. So now the kernel is just continuing, as I can press enter here. Now that everything is working on that side, let's first make sure that our kernel driver is also installed on it. Let's transfer our file over there. By using SCP, we could easily transfer files over there. Now, what we do is just SCP and then the port number and then the program, and we are just writing it over. Once that is done, it has been overwritten over here. We have now our program over here on this side. Now I'll make it clear so that it's easier to see for you. If we look at that, we have a program over here. And if we do lsltr, we should see that this program has root privileges. We are going to change that in a minute so that doesn't have any root privileges. Now we can just easily try this out by doing program write hello, and we should see there's no driver yet. So what we need to do is make sure that we have a driver. So for that, we'll do insmod and install the driver that we have over there, which is the same driver. Once you have done that, it will say to you, invoke the node to make sure that the driver is accessible. We'll do that right away, copy that and paste it in there. Now our application should be able to write to this. Now you can see we are able to easily write to it, and this is the basic stuff, right? There's nothing special yet. Now, if we just open in here again, and I'll press Ctrl C, if you remember in our code, you could see that this was opening a new shell there, right? So if that is correct, we should be able to see that over here. If we do lxps, we should see a second process. Exactly, that's correct. We have a second shell over here. If I exit this one, and that is not possible since we are debugging. So I'll continue the process and type in exit over here again. And if I'm correct right now, we shouldn't see the second one, which is correct. That process has disappeared. Now, we need to make sure that, because this is now running as root, we need to make sure that it doesn't run as root. There we have another one. So let's have a look at that quick. I already did that, so there's no need to do that. But to give you an idea, in there, we also have some files, which is like the file that we see over here. And here you can see this has the user fuzzing and doesn't have much privileges, right? If I do right now ID over here, you will see I have the root privileges. Now the idea is switch over to this user and start doing this. Before we do that, we need to first make sure that this driver is also accessible by any other user. So I'll do that quickly by changing the permissions of the driver that we just added to this system. Now, since this is done, we should be able to switch over to the normal user to fuzzing. And if I do ID, you can see now we are the user fuzzing. If I try to access, like for example, for the root folder, you can see permission denied. We cannot access because this is all accessible only by root, and this is not accessible by us. So if we just do this and then ls ltr, we should see that the root folder is only accessible by the root user. Now, let's go back, because as I said, we are now a new user, and now we are going to look how we can do the privilege escalation. I'll go back to the folder earlier, which was in the cd/root. You might ask yourself, why can we access that file? That directory is owned by fuzzing, so we can access that one. So if we just, again, check this, this is executable by fuzzing. And we'll start doing this in the debugger right now. Before we can continue, we also need to be able to load the driver over here. So first, let's exit over here and become the root user again. I'll clear this up so that you can see this much better. So first, what we need to do is make sure that also our driver is accessible through because we loaded the kernel over here, but the driver we inserted later. So we need to make sure that the driver is also accessible. So I'll type in section and then .text, and then take the address of the text section, which is where the code lives, and start adding this also to our. We can do that by typing add symbol file and then home/kernel fuzzing and then course kernel driver and then the driver itself, the compiled driver file. Now I'll press enter, and it will ask me to load it. We did something wrong. We also need to add the address behind it, and I did that now, and it will ask us, would you like to load the text section of it? I will say yes. Now, since this is possible, we can now put a breakpoint on driver underscore write, as we saw in the code. We can go back to the drivers code. We see here driver open, driver read, and we had a driver write. And we want to put a breakpoint on driver write, because we would like to see once we are writing to the process, we would like to see if that works. So let's put a breakpoint over there, and now we'll continue this process. I'll switch over to the user fuzzing, and we'll check again. We have this permission. We are now the fuzzing user. Let's now interact with our kernel driver. We'll use the write and then type in hello. Doesn't matter much. You can see we directly hit our breakpoint over here. That means right now we should be able to access all the process structures. Now I'll just do very simply p and then $LX _ current and then get the PID of the current process. You can see it is process 174, and we are going to continue. We hit our breakpoint, which is quite great. Now, the only thing that is left is that we need to get the credentials, the structure of the credentials. If we now access LX current, this is the process that we are accessing right now, which is the shell, which is this process that we are accessing right now. And what we are going to do is get the credentials of this current process by typing as cred is of this current process LX current, and it has a structure called cred. We should be accessing the creds by typing $cred and that should give us all the credentials over here. Now you could see here very simply, I forgot the $sign because this is a variable that we created and it didn't recognize it. So once we put the $sign there, it's using a variable. Now that we can access the credentials of the running process right now, we put a breakpoint right at that moment. We should be able to access it right now. Now, if we look at here, we see something interesting. We see the GID, and that you can see over here, and you see the value there, and you see the UID, which is a value over there, and the SUID and many other stuff as well. Now, it's actually quite simple, because if we override these values with a 0, which was the root user's value, we should be able to escalate our privileges. So let's try that out very quickly, and I'm going to do that simply by just typing that in. We'll set the UID.value. Yeah, that's that one. And then I'll continue with the GID, which is the group ID. Let's modify that one as well. And then change the ones, the EUID. We'll just change everything that we can change and then continue the process. And if you remember, our process itself is going to drop in a shell. So that shell should be in a root shell. So once we have finished this, overwriting everything and continue the process, and the code will hit the new, the system execute a new shell, it will get the new privileges that we assign to it. And this is also the steps that people are doing during kernel exploit development. And this is also the steps that we will do in more detail and more use real vulnerabilities. We'll exploit bad binder and also other binder vulnerability in the course. So this is just as an introduction for you so that you have an idea how this process credentials work. And in general, what happens is in every kernel exploit, what we are trying to achieve is escalate our privileges. And we do that typically by overwriting the process credentials. On other systems, for example, you could also add a new user to the user/etc/password file. You can add a new user there with a new password. Depends on the type of vulnerability you have, but in a read-write primitive, which is the typical way right now to exploit a kernel vulnerability. So I'll add this over here and press continue. And as you can see, this process continued. We should have a new process over here. So if I do ID over here, as you can see, our user has changed. The only thing that hasn't changed is the groups, which I have probably used a wrong one for. But even that one is quite easy to do. But let's do something very easy. Let's go to the root folder as we tried earlier and try to access it. There's no error anymore and we can access it. If I exit this, the process will exit and will become again the old user. Now, this is how privilege escalation on Linux works. Actually, nothing more than values within the task struct there. So just to make it simple, a little bit simpler, is that we have a structure for every process that's running, which is the task struct, and the task struct contains a pointer to the creds. So every process has also credentials. These credentials are nothing more than value. But if you have like kernel code execution, and that can read or write for you, especially write, you should be able to write values in the kernel itself. If you write a process credential to 0, like what we did in here, you achieve privilege escalation. So this is it for the video, and I hope you liked it. So now that we learned how privilege escalations on mobile devices and other type of Linux systems work, I also want to highlight that we are giving a training at Black Hat USA 2024. And this is a special type of course where we will teach the full chain exploitation of mobile devices. For example, we'll show you how you can actually abuse vulnerabilities in userland applications, also abuse kernel vulnerabilities, and then get full access remotely to a mobile device. This is a very specialized course. If you cannot attend like Black Hat, we also are going to release our Android kernel fuzzing and exploitation course by the end of August. So you can find the link in the description below and to register already for the course. This will be a pre-sale of the course, so make sure that you, or if you are interested in this topic and you want to learn how to do this, we have like real-world examples, real-world vulnerabilities that you will learn how to exploit and learn how to build full chain exploits that achieve root access against Android devices. Thank you very much, and also make sure that you hit the bell button and make sure that you leave a like and comment below in the section. Let us know what you think of this video and what type of topics you want to see in the future, and also let's discuss in the comment about any other stuff about mobile security and cybersecurity in general. All right, thank you very much guys, and this was it for today, and let's see you in the next video in the coming week.